Welcome to this new video where we will solve the heaters problem. We have a horizontal line, in it we have houses. For example, here the houses 1, 3, 4, 6, 8. And these houses have to be heated. For that, we have heaters at certain positions. For example, at positions 1 and 5 here. And we are given the ability to modify their radius. The more we increase the radius of a heater, the more it covers houses. And the problem says that we need to find the minimum radius that we give to the heaters to cover all the houses. For example here, they have a radius of 0, only house 1 is covered. We increase the radius, now houses 1, 4 and 6 are covered, but 3 and 8 are not. We increase the radius again, houses 1, 3, 4 and 6 are covered. We increase again, now all the houses are covered, so the minimum radius is 3, we return 3. Note that you can neither modify positions of heaters nor add new ones, and the same radius is applied to all the heaters. Okay, how do we solve this problem? We can think of a brute force solution that works as we did with the example now. We start with a radius of 0 and we keep increasing until all houses are covered. For that we need two structures, a set of uncovered houses and an array that contains the boundaries of the range covered by each heater. In this example, uncovered initially contains 1, 3, 4, 6, 8. But we remove houses on positions where we have a heater because they are already covered, even with a radius of 0. House 1 gets removed. And our heaters are in positions 1 and 5. We initialize their range at 1, 1 and 5, 5 respectively. Because their radius is 0, they cover their position only. Now first iteration, we increase the radius. We modify the ranges by decrementing the left boundary and incrementing the right boundary. Heater 1 now covers range from 0 to 2 and heater 2 covers from 4 to 6. The new covered positions are 0, 2, 4 and 6. We remove houses that are in these positions. The uncovered set isn't empty yet, we continue. We increment the radius, the ranges become 1 is 1 to 3 and 3 to 7. In newly covered positions, we can find house 3. We remove it from uncovered. We continue, we increment the radius, the ranges become minus 2 to 4 and 2 to 8. In newly covered positions, we can find house 8, we remove it. Uncovered set is empty now, we return radius, it's 3. We need a radius of at least 3 to cover all the houses. In code, uncovered houses is the difference between the set of houses and the set of heaters. Remember that we remove houses that are already in positions of heaters. Then, we create the array of boundaries of heaters. For each heater, we put an array of two elements. They represent the left and right boundaries. At the beginning, they are both equal to heater, the position of the heater. Now radius starts at 0, then while there are still elements in uncovered, we increment the radius, then for each heater, we decrement the left boundary, and we increment the right boundary. We also remove from the set newly covered positions, which are the new positions that we've been able to reach. After the loop, we return the radius. For the time complexity, we put n as the number of houses, m as the number of heaters, and r as the final radius. We have n for creating the set of houses, m for creating the set of heaters, n for calculating the set difference, and 2m for creating the ranges array. Then for the loop, at each iteration, we're incrementing the radius, so the number of iterations is equal to r, the final value of radius. At each iteration, we're traversing the m heaters while doing O of 1 operations. In total, we get T of nmr is equal to 2n plus 3m plus r times m, which gives an O of n plus r times m time complexity. We can say that this algorithm is output sensitive. Its running time depends on the output, r in our case. And for the space complexity, we have n for the set of houses, m for the set of heaters, and 2m for the ranges array. We get n plus 3m, which gives an O of n plus m space complexity. This solution is not the best one, because we have cases where it's really slow, cases where houses are far from heaters. We will need to do a lot of iterations. This is why we will see another solution. But before, please take some seconds to suggest problems that you want me to solve. Tell me in comments. The idea of the second solution is that, because all the heaters will have the same radius, a house will necessarily start being heated by its closest heater, because when we keep increasing the radius, its closest heater is the first one that starts covering it. What we can do with this information is that, for each house, we calculate the distance between it and its closest heater, and after doing so, we take the maximum among the distances. It represents the smallest radius to cover all the houses. Let's try it with our example. House at position 1, its closest heater is the heater at position 1, the distance is 0. House at position 3, its closest heater is at position 1, or the one at position 5, same distance, is 2. House at position 4, its closest heater is at position 5, the distance is 1. House at position 6, the distance is 1. House at position 8, the distance is 3. We got all the distances, the maximum among them is 3, so 3 is the smallest possible radius to cover all the houses. Any smaller radius won't be enough to cover the house at position 8. In code, we create an array distances, then for each house, we calculate the distance between it and its closest heater, and we add it to the array distances. For that, we create a variable minDist initialized to infinity, then for each heater, minDist becomes the minimum between itself and the distance between the actual house and the actual heater. Abs means absolute value. After the loop, we just return the maximum distance, which represents the smallest possible radius. We can even keep track of the maximum value, which is the radius, while traversing houses, to avoid losing space on storing the distances. For the time complexity, the outer loop is doing n iterations, the number of houses. The inner loop is doing m iterations, the number of heaters, and we're doing O of 1 operations inside. We get an O of n times m time complexity. And for the space complexity, we got O of 1 because we're not using size-related variables. Let's see if we can optimize this solution. Here we are performing a search on the array of heaters multiple times. We're traversing all the heaters. We're performing linear search, which costs O of m. But by sorting the heaters, we can search for the closest heater to a particular house by using binary search, which costs O of log m. We keep going towards that house at each iteration while keeping track of the minimum distance. For example, we have this sorted array of heaters, and we want to find the closest heater to house 16. Mid is left plus right divided by 2. We got 4, the heater at position 9. The distance between 9 and 16 is 7. We got a new smaller distance. And because heaters of mid is smaller than house, we drop the whole left part and focus on the right part. Mid is 5 plus 8 divided by 2, which is 6, heater at position 13. The distance is 3, we found a new smaller distance. Heaters of mid is smaller than house, we go to the right part. Mid is 7 plus 8 divided by 2, which is 7, heater at position 17. The distance is 1, we found a new smaller distance. Heaters of mid is greater than house, we go to the left part. Now left exceeded right, we finished our search. We found that the smallest distance between the house and a heater is 1. We return 1. In code, we put left and right at extremities of the array, at indexes 0 and m-1. We initialize minDist to infinity, then while left is smaller than or equal to right, we start by calculating mid-index, left plus right divided by 2. After it, we check if we replace minDist. MinDist becomes min between its actual value and the distance between the house and the heater at position mid. After it, we check if we go to the left or to the right part. If heaters of mid is smaller than house, we go to the right part. Left becomes mid plus 1. Else, we go to the left part. Right becomes mid minus 1. After the loop, we return minDist. Know that I could directly use the Python bisect function for binary search, but I wanted to show you how to adapt it to this problem. To apply binary search, the array has to be sorted, which is not necessarily the case. It's not mentioned in the problem description that the heaters array is sorted, so we start by sorting it. Then we traverse houses while keeping track of the greatest distance between a house and its closest heater. We return it after the loop. It's true that sorting an array costs time, but it will give us the ability to search in O of log m time only by using binary search, instead of O of m with linear search. For the time complexity, we have O of m log m to sort the heaters, then for the loop, we're traversing n houses, while applying binary search on the array of heaters, which costs O of log m. In total, we get O of m log m plus n times O of log m, which is O of m log m plus O of n log m, which gives an O of m plus m log m time complexity. And for the space complexity, it depends on the space complexity of the sorting function. We still have a solution to talk about. In reality, what we can do with binary search is to find between what headers our house fits, between closest ones obviously. For example, with our last example, house at position 16 fits between header at position 13 and header at position 17. And after finding this position, we compare between the distance between headers of I and house and the distance between headers of I minus 1 and house. The smallest value is the minimum distance, 1 in our example. And the trick is that to find the closest headers to the next house, we just keep incrementing I until headers of I becomes greater than or equal to the house. Let me show you an example. We have these houses and these headers. We add two headers on infinity and minus infinity to avoid going out of bounds. The first house is 3 and the first header is 1, smaller so we increment I. Now headers of I is 4, greater, we stop. We found where house at position 3 belongs. The distances between house and headers of I and headers of I minus 1 are 1 and 2. The smallest one is 1, radius becomes 1. Next house is at position 12. We increment I, we increment I, we increment I, and we found the right position. Distances are 3 and 2, minimum is 2, it replaces radius. Next house is at position 20, we increment I, and we found the right position. Distances are 3 and 4, minimum is 3, it replaces radius. Next house is at position 21, we're already at the right position of I because the headers of I is greater than 21. Distances are 2 and 5, minimum is 2, it's not greater than radius, it doesn't replace. Next house is at position 22, same thing, we don't increment I. Distances are 1 and 6, minimum is 1, it doesn't replace. Next one is at position 31, we increment I, we increment I, we increment I, and headers of I is now greater than house, we stop. Distances are infinity and 2, minimum is 2, it doesn't replace radius. We finished traversing houses, the value of radius is 3, so we need a minimum radius of 3 to cover all the houses. You can see that we were traversing houses and headers in a sorted way, but the input is not necessarily sorted, so we need to sort both arrays before starting. In code, we sort houses, we add infinity and minus infinity to headers, and we sort headers. Now we initialize radius to 0, I to 1 to skip minus infinity, then for each house, we keep incrementing I while headers of I is smaller than house. After doing so, the distances are the distances between house and headers of I and headers of I minus 1. We take the minimum among them, it represents the distance between house and its closest header. After it, we see if we replace radius. Radius becomes max between its actual value and min dist. After the loop, we just return radius. For the time complexity, we have n log n to sort houses and m log m to sort headers. And for the loops, even if we have nested loops, the inner loop won't always do the same number of iterations. We just know that in total, the inner loop will do at most m iterations because each header is traversed once. Plus n iterations to traverse the houses, we get m plus n for the loops. In total, we have n log n plus m log m plus n plus m. It gives a time complexity of O of n log m plus m log m. And for the space complexity, it depends on the space complexity of the sorting function. This solution and the previous one both have a good time complexity, but the second one gave better results on LeetCode. We reached the end of this video. I hope that you understood all the solutions. If you enjoyed, like and subscribe to the channel, and see you in the next one.